All right, hi guys, I'm back. I got cut off, and so I am still working on this worksheet. And so I had found this worksheet online, Integrated Algebra for 3 Exponential Growth and Decay. I just did a search. This is from a program called CUDA software. And so it was just an online worksheet that someone posted, and I'm using as a review. So we were back here, and I got cut off because I bumped something. So I'm going to start again with number 13. And I was talking about 13 where you have to sort of work backwards this time. We're still going to do everything the same, but we want to talk about what happened 35 years ago. So today, the menu cost is $25.25, and it's been increasing 4% each year. So that's sort of like an average increase. And so how much did it cost him 35 years ago? Okay, so we have to talk about this problem like it's the future. But 35 years ago, our time is going to be negative 35. So we're not actually going to be looking at this as something decreasing. We're still going with growth because it's telling us that it's increasing at 4%. Okay, so we're going to look at this, that it's building. My multiplier is 100% plus 4, which is 104%. And so I'm going to change that to a decimal of 1.04. The equation A of t, the amount over time, is going to be the initial value, or the cost now, which is $25.25, times 1.04 to the power of time, okay? And then what is the value of n in this case? Well, I guess I'll make that, let me make this an n. They're using n for time, which is fine. And so I'll go back and change that. And so n for us is going to be negative 35. So what is the amount over negative 35 years? And that is going to be 25 times 1.04, but this time it's the power of negative 35. Now, this is going to be a crazy number, but by putting a power of negative 35 on there, if you remember, that is going to flip it and make it 1 over 1.04 to the power of 35. So we'll just put this in the calculator for sure. Let me put this up here. And so I have 25 times 1.04 to the power of negative 35. All right, and we get that it was about $6. I'm going to round that to $6.40. And so after 35 years, the restaurant cost is $6.40 for that meal. Okay, so we've got a gallon of milk and it costs $3, and now the price is increasing 10% each year. How long before the gallon of milk costs $10? So this is a little different. I'm asking you to give me when this happens. So again, this is growth because it is increasing. My multiplier is 100 plus 10, so 110%. And that'd be 1.10. And so write the explicit equation. It would be the amount over n, we'll use n since they use that, is equal to $3, that's how much we start with, times 1.10 to the power of n. So that's my basic equation. And if they said, well, what happens in 5 years? I'd put a 5 here. What happens in 10 years? I'd put a 10 here. But they're asking me, when does it cost $10? And so the 10 or the $10 goes in for A of n is 10. It goes into the answer. So I'm going to have 10 equals 3 times 1.10 to the power of n. Now, if you've just been working with exponential growth and decay and you don't know logarithms right now, then the most you would do is you would type this into your calculator, almost like you'd be filling in a t-chart, and you'd be trying to figure out what it is. So I would take it to the power of 5. And that's $4.83 with the power of 5. So that's not enough. So I'm going to go back up. I'm going to change that. I'm going to jump to 10, and I get 778. Okay, so it's still not enough time. So that's 10 years. So let's jump to 15. Maybe I'm overdoing it, and I overdid it. Okay, so this might be something that you could make a t-chart to. And you have your, in our case, it's n and the amount over time. And so we did 5 years, and we did 10 years, and we did 15. So in 15 years, it was 1253. We had 10 years at 778, and we had 5 years at 483. And the reason I'm taking the time to show this chart is if you were asked to graph it, it's simple. If you were asked to graph this explicit exponential equation, it's simple. You just pick some x values and plug them in, and you get the values. This is a real world problem, so we're not using negative time unless we want to know what happened 10 years ago. Then we put in negative 10. So I know that I'm somewhere between 10 and 15. So I'm going to go back up and maybe I try 12 years. In 12 years, it's still under. In 12 years, it's 9.42 if we're rounding. So I am going to go to year 13 and see if we get it. Oh, got it. Year 13, $10.36. So it will take about 13 years. If you wanted to get more exact, you would say, oh, between 12 and 13 years. And we could start playing with these numbers, 12 and 13, 12 and a half, and see what's closer. To really, truly do this problem, and I like to do this because this is a preview about what we're going to do. To really do this problem, it would involve logarithms. And like I said, you might not have been taught logarithms yet, but when you get to it, you'll come back and solve problems like this. So if I'm solving this using logarithms, how do I know to use a log? Well, I know to use a logarithm because logarithms solve for unknown powers, and I definitely have an unknown power here, which is n. So I'm going to solve using my order of operations by dividing out the 3 first. And so I have 10/3 is equal to 1.10 to the power of n. And I'm leaving this as a fraction just because I don't want to round it. So fraction or mixed number is fine. And then to take this and find the unknown power, I'm going to take the log of each side. And again, this is log base 10, something that you learn when you work more with logarithms. And by taking the log of each side, there's a product property. So I have log of 10/3 over here is equal to log of 1.10, but that power of n is going to come out and become multiplication. So it's n times a log of 1.10. And following just basic order of operations, if I want to solve for n and it's n times something, you have to remember that log 1.10 is a number, I just divide by the log of 1.10 on both sides. Again, this is something that you might not have covered yet, so I'm just showing it in case, or you can come back to it. When I put this in, I want to remind you that the logs cannot cancel out. You actually have to type in each thing individually. So let me show you what it looks like in the calculator. I'm going to go to log, and it's 10 fraction 3, or 10 divided by 3. And notice I'm closing those parentheses, and then I'm dividing it by log 1.10, and I'm closing those parentheses for good measure. And we get it to be 12.63. So we then can see that, hey, n is approximately 12.6. I better round it up to 12.633. And someone might say, oh, you're breaking your, 33. Might say you're breaking the rounding rules, but if I put it in at 12.6 or 12.63, I'm actually going to be under $10. So I actually have to break a rounding rule and go up just a little bit. So there's a more exact answer. 12 years is too short, 13 is going to be over. Okay, so now they have taken away the steps to writing these problems. So it says write the explicit equation for each and then solve them. So we start out with bacteria. We have a colony of 180 and it's at noon. It is growing at a rate of 22% per hour. And we want to be careful because it might be growing per half hour. And so we have to watch how many half hours we have. All right, how many will be there at 8 p.m.? Okay, and round to the nearest whole bacteria. So our formula, the amount of bacteria over time, is equal to our initial amount. And that's what anytime we're doing this, I want you to remember that the amount over time is equal to the initial amount. So what's your population? How much money did you start with? How much was it worth? Times a multiplier to the power of time. that's what our exponential growth and decay looks like. Initial amount, multiplier to the power of time. Since this is growing, my multiplier is 100 plus 22, so 1.22 to the power of 8. We started at noon, 8 hours later would be 8 hours. And again, to solve this, there's my equation, okay? And then to solve this, I am going to put it in my calculator. 180 times 1.22 to the power of 8 is equal to a lot of bacteria. So the amount over 8 hours is 1,756.8. And it said around the nearest whole, so that would be in 8 hours, or at 8 p.m., there are 1,757 bacteria. Okay, all right, so a comic book originally sold for 35 cents and appreciates 10% per year. So appreciate is increasing. Didn't mean to scribble that out. And 35 cents is what it was worth. What will it be worth in the year 2020? So we're talking 50 years. Round it to the nearest cent. Okay, so the amount over time is equal to 0.35, and it's growing at 10%. So 110% is 1.10 to the power of 30. So it's growing 10% per year, but you know, sometimes we're talking about populations and it might grow per decade. So that's something you want to consider. So we are going with 50 years. And that doesn't really look like a 5. Okay, and so again, I'm going to put this into a calculator. 0.35 times 1.10 to the power of 50. And we get that comic book, so over 50 years, is $41.09. So it would be, the comic book would be $41.09 after 50 years. All right. Inflation, meaning money going up, prices going up, is at a rate of 7% per year. Okay. So today, Janelle's favorite bread costs $3.79. What's the cost going to be in 10 years? So inflation is the increase, so it's growing, and here's my initial amount. So the amount over time is equal to the initial amount of $3.79, and then it's going to be at 1.07. So really be careful with that. It's 100 plus 7, which is 107%. One of the mistakes people make is they want to say that it's 1.7. So it's 1.07 to the power of 10 years, so 10. So again, we'll plug that into our calculator. 3.79 times 1.07 to the power of 10. And that would be $7.46. It didn't specify, so I'm going to go ahead and round it to the nearest penny. So again, in 10 years, the bread will cost $7.46. Okay, so we have another problem here. Ryan's motorcycle is now worth $2,500. Unless it's a collector's, it's not going to appreciate, it's going to depreciate. So that means we have decay here, 12% per year. He bought it 4 years ago. What was the cost when it was brand new? Okay, so it's now worth $2,500. So we have to work backwards here. So there's a couple ways of doing this. You could do it like we did number 14. I'm sorry, where is it? We could do it like we did number 13, where we have the cost now, we want to know what it was before. Or we could do it like we did 14, where we say when is it worth this value, and we would have an unknown amount here. But we're going to go ahead and we're going to talk about using that negative power. So we're going to start with the amount over time. And so we are talking about it being worth $2,500. Now remember, it's depreciating with a D, and so it's going down 12%. So we take 100 minus that 12 and we get 88%, which is 0.88. The difference here is this is not the value it was initially at. This is the value that it's at now. So we want to take that back 4 years. Okay, so we'll put that into the calculator. 2,500 times 0.88 to the power of -4, and we will see that 4 years ago this motorcycle was worth $4,168.78, rounded to the nearest dollars. So new, the motorcycle was $4,169. Okay, so we have a couple more problems here on a new page. So let me put this up for you to see. And so it says a bank account starts with $100 and earns 4% annually. How much money will there be in the account after 12 years, assuming no transactions have occurred round in the nearest cent? Okay, now there is other ways of doing interest. There's something called compound interest, but we're just going to do some basic annual interest and base it on that. But yes, we can get into interest problems where we have some other formulas to use for compound interest. So we are starting with our initial amount, and it's growing at 4%. So 100 plus 4 be 104%, or 1.04 to the power of 12. So that is going to be the amount after 12 years. And so I'm going to go ahead. So just having $100 and investing it in something with 4%. Let's see how much we have. 1.04 to the power of 12. And we are looking at $160.10. So the amount after 12 years is $160.12. So that's what the meaning of the problem is. I will have $160.10, sorry, in my account after 12 years. So that's not bad, $60 for it just sitting there. Okay, Jim received $2,000 in a loan from his bank, and the loan accrues, meaning it's gaining interest of 3%. Every 3 months. How much will Jim owe the bank after 4 years, round in the nearest interest? Again, we are going to use exponential growth here. So we're going to start after 4 years. Now that's different. It's accruing 3% every 3 months. So in 4 years, we have 12 3-month intervals. So the time is going to be 12 because there are 12 3-month intervals in 4 years. Okay, again, you could also look at this as a compound interest formula, but we're looking at it as exponential. So the amount over 12, so it's not 12 years, it's amount over 12 times that this is compounded. And so we are starting with 2,000, and it is going to be a power of 1.03. Okay, how much he owed for the loan plus an extra 3%, and this is going to go on 12 times. So that is a little bit different there. So we start with $2,000. Let me try to get that out of the light. Times 1.03 to the power of 12. And that is going to hurt my piggy bank. The amount accrued over 12 of these 3-month intervals is $2,851.52. So that is how much he would owe the bank in total if this loan sat there and there were no payments made. So you can see, even though it was 3% interest, it was every 3 months, and that 3% interest ended up costing me an extra $851 over 4 years. Okay, each year the local country club sponsors a tennis tournament. Play starts with 128 participants. During the round, half of the players are eliminated. There's a little typo there. Half the players are eliminated. How many players remain after 5 rounds? I hate to compare this to Half-Life, but it is much like a Half-Life you would see in a biology or a chemistry class. So if we're losing half the players, we're losing 50%. And so 100 minus 50% is 50%. So we start off with, and this is after 5 rounds, and it says during each round, half the players are eliminated. So amount over 5 rounds, the time of 5 rounds, is 128 players times 0.5 to the power of 5. Remember, that 0.5 is from our 50% loss. So we would come in and we would take 128 times 0.5 to the power of 5. And we get that at that time, there would only be 4 players left. So 4 players or people remain after 5 rounds. Okay. John's curious how much money he can make in a month. He hopes to double the amount he makes each day. So how much money would he have made on March 31st? Okay, so he's starting on March 1st. How much money can he make in a month? Oh, he makes a penny. I missed that. He makes a penny on March 1st, and he hopes to double that amount he makes each day. Okay, well, you would look at this and say, well, that's not really that big of a deal. But we're talking about 31 days, and we're doubling it. So it actually grows faster than you realize. So the amount's over 31 days, and our initial amount is a penny. So I'm going to write that in dollar form, okay? So my answer is going to be in dollars. If I wrote it as a 1, we'd be talking about something different. And he is going to double it. So my multiplier is 2. It is 100% of what I had plus 100%. So that is 200%, which doubles it. And it is going to go to the power of 31. So if you are doubting the power of a penny, don't, because we are going to see how crazy this is. So we are doubling it 31 times. 62 cents. Now that's not amazing, but can you imagine that over time? So we had 1 penny, we're going to double it every time, and so we are looking at having 62 cents. The power of a penny. Okay, so that is the first review. This was all on exponential growth and decay, and I hope it was a good review. You've practiced these skills. There are definitely a couple ideas that were a little different than what we had done in class, but I think it was worth our time to look at it.